Okay, so part two of brute force search. Last time we looked a little bit about how to use for loops to loop over existing data and systematically list all the possible combinations for sets of things. And this time we're going to talk about how you can think about any problem at all as a problem of search. Namely, searching through all possible answers to your problem and testing each one until you find it. This is a classic puzzle called the 8 queens puzzle. The puzzle is, can you place 8 queens on a chessboard so that none of them threaten each other? If you don't know, the way that a queen can move is illustrated here. A queen can move as far as she wants in any direction, including diagonals. So if I just gave you this puzzle, it's very likely that you would start thinking about it like a puzzle. You'd place queens and you'd maybe backtrack and kind of figure out what you think the solution is. What's nice about brute force search is you don't have to be clever. That's the whole point of brute force search. So what we could do is literally loop over every single possible way of arranging queens on the board until we find one that works. This is why brute force search is often your first attempt at solving a problem. It's because it really doesn't take very much thought to implement it, because you don't need to know about chess strategy, you don't need to think about anything clever. All you need to do is loop over possibilities. And if it works, great, you've answered your question and you're done. If it doesn't work because there's too many possibilities or they're too difficult to list or something like that, that's when you kind of back up and try and find a different approach. So to have the text on the slide by itself, brute force search, which is also sometimes called exhaustive search, is the process of looping through every single possible answer and testing each one until you've found it. And it's called brute force because you're not doing anything smart. You are just putting in a lot of effort. So here's another kind of straightforward example. Can you find integer solutions? So that is integers for x, y, and z, which satisfy this equation. This type of equation is called a Diophantine equation. And this particular example actually was unsolved until 2019 when a solution was found using computer search. So that's why I selected this as an interesting example. So you tell me, what is it that we're going to loop over if we're looping over all possible solutions to try and test for one that works? So the answer is we're looping over all possible sets of values for x, y, and z. So this isn't particularly systematic, but you could plug in 0, 0, and 1, and 0, 0, and 2. And like obviously you and I know that this would be a silly combination to consider because there's no way that 0, 0, 1, when you cube each of them and add them up, is going to add to 33. But again, we're not trying to think too hard about how to cleverly solve this. We really just want to set up some loops that will loop over all the possibilities. So just to be clear, as we're looping over possibilities, how do you test to see if there's a solution? Well, for this problem, all you do is plug them in and see if they end up equaling 33. So if we wanted to check 23 and 4 and negative 22, when you cube them and add them together, you do not get 33, and so that doesn't count as a solution. So we would continue looping. So to use brute force search, you need a good way to systematically generate every possible solution, and you need a good way to check them. And ideally, checking them is going to be relatively fast. Otherwise, brute force search is going to be too slow overall. So how can we systematically generate all the possible combinations of x, y, and z? We can have 3 nested for loops. So we can loop x from 0 up to a large number, and y from 0 up to a large number, and z from 0 up to a large number. So this actually probably isn't the best. One thing this misses is it's going to miss solutions that have a negative value. A second question you might ask is, well, how large is large enough? How do we decide? Should it be like integer.max value? Should it be something else? Well, first let's solve the problem of negative numbers. Instead of looping from 0 up to a large number, you could have each one start at a negative large number and loop up to a positive large number. So let's start thinking about the size of the search space for a minute. How large should our large number be? So if the large number is 100, then that means each of these variables is going to loop over 201 values. The reason why 201 is because it's going to go from negative 100 down to or up to negative 1, and then it'll hit 0, and then it'll go from 1 to 100. So that's 100 values, that's 100 values, and then the 0 counts as the 201st value. So if each of our variables loops over 201 values, how many different combinations is that? It's 201 times 201 times 201, so that's 8.1 million. For this particular problem, that seems well within the range of possibilities that a computer could reasonably tackle, that in fact your like home computer could reasonably tackle. But the problem with combinations is they grow rather quickly. So try another one for yourself. So what if the large number is 200? How many values are you going to get then? Think about it for a second. So each of the variables will take on 401 values, and that's going to be 64 million. So now that's getting large enough that maybe it would take a while to run on your home computer. And 200 isn't a very large number to consider. So let's step back for a second and think about the question in general of what is a search space. So the term search space refers to all of the possibilities that you might want to search through. And the reason it's referred to as a space is because you can think about the possibilities as arranged in a coordinate system. So in our example, we had 3 possible values, x and y and z, and we were selecting each of them independently of the others. So that would be a 3-dimensional search space because we have 3 numbers and each of the numbers can change independently of the others. The size of the search space is going to be something like the volume of space that we're looping over in the 3-dimensional space. But as you can see, it's very easy to come up with larger dimensional search spaces, and the size of the search space can grow quite quickly. So a good takeaway lesson here is if you're going to loop over all the possibilities, you'll use some nested for loops, but pause and think for a minute about the smallest and largest values that it makes sense to loop over, because it's really, really easy to just start at 0 and go up to something in situations where that wouldn't make very much sense. So what about the 8 queens problem? Think again about what we're looping over and see if you can answer the question for yourself. What dimension is the search space, and what's the total size of the search space? So the dimension of the search space is always 8-dimensional because we are choosing 8 things, each of which can vary independently of the others. But the size of the search space kind of depends on the range of values that we're choosing. And there's different ways to think about the puzzle. So here's one way to think about it. There's 64 total spaces on the board, and I'm placing 8 queens. And if I don't place any restriction at all on the possibilities, I could place each of the queens in 64 possible spots, and so that's 64 to the 8th power possible configuration. So that is 281 trillion. That is probably not within the range of feasible search for your home computers. Just to give a sense of what it would look like, though, this represents one possible arrangement of queens. So I've got 8 different queens I'm placing, and for each queen I have a different location that's selected from the board. It's not totally obvious. I mean, it would be very easy to construct a random search using this approach. All we do is we generate a random location for each one of these and then test it. But be careful, because random search is not the same thing as brute force search. Brute force search requires that we systematically visit all the possible configurations. And if we're generating random locations, that's not systematic. Random search is actually a type of search that you could use, and there are some conditions under which random search will actually perform very well. But I don't want to think about that right now. We'll come back to that at the end. So let's consider a different way of making our selections. Let's assume that we're going to place a queen in every single column, and then all we have to choose is the row for each of the queens that we're going to place. So now, each column contains 8 possible rows. If we're not going to place any restrictions on the rows, then that's 8 selections, each of which has 8 options, so 8 to the 8th. So that's 16 million. That's a heck of a lot better than 200 whatever trillion I said before. And one way you could choose to represent your arrangement would be like this. You could have an array that's length 8. You could let the index of the element represent the column number. So now we are representing every single column once. And then the number in the array at that index would represent what row we've chosen. So here we're imagining in column 0, we're going to place in a queen in row 6. And then in the next column over, we're going to place one in row 2. And then in the next one over, we're going to place one in row 3, and so on. You'll notice here that this configuration has actually selected row 3 for columns 2 and 4. And so you and I know right away that those 2 queens are going to threaten each other because they're horizontally, they're in the same row, so they're going to be sort of horizontally threatening each other. But again, like as long as you're able to reduce the size of your search space enough, it might not be worth it to get more clever than that to try and eliminate possibilities that you and I know aren't good ones to consider. You can just let the computer loop over them and then reject them when you test to see if they're solutions. So when should you be clever? I would say do a rough calculation on the size of the search space and see whether you think it's like astronomically large. For this 16 million, you may not have a good intuition about whether that's too large or not. So you could program it and see, because usually these things are pretty quick to program. If it turns out that your search space is too large, then what you can do is you can start thinking about more clever ways of selecting the options so that you eliminate certain options that you know you don't want to consider. And that would be a way of reducing the size of the search space. So in code, it could look something like this. You'd have one for loop that ranges over all the possible row values for one of your queen placements. So this outer loop might be all the possible rows for the queen in column 0. And then the next loop would be all the possible rows for the queen in column 1, and so on. So then once you've collected values for row 1 and 2 and 3 and 4 up to 8, you could feed those into a method that tests if that represents a solution, and if it is, that you could display it. We're going to look at this problem in class next time. So this is sort of the bonus problem for today. I'd say try and tackle it however you think is best. As a preview of next time, the data structure that you use to represent your board configurations can make the task of checking whether or not queens are threatening each other either very easy or quite difficult. So think hard before choosing your data structure. And in particular, imagine how would you figure out whether two queens are threatening each other? What kinds of looping is necessary? Is any looping at all necessary? And think about a couple of different ways of representing that same information before you commit to one. If you're not sure what I'm talking about, then don't worry at all about it, because that's going to be the topic for next time.